Hello everybody, today I'm going to show you guys how to calculate or derive the equation that will calculate the length of a certain parametrized graph. So here we have a parametrized curve on a 2D coordinate, y-axis and the x-axis. So we have this curve, any arbitrary parametrized curve that is unique in terms of its being or we can call it a smooth curve, right? So that it will not intersect itself, and all of the is differentiable at any point, at any particular point along the curve. Okay, so we have this curve. We can call this curve some. We can put in some in a vector function. So we have, say, r vector rt equal to for the x component, we may have the function, the value x is being dictated by the variable t. You can think of it as time, or it's just any parameterizer. So you have x of t, you have y of t. So if you go, this is 2D case. If you have a 3D case, three-dimensional coordinate, you may have like a z of t there. So we have rt equal to this vector notation xt and yt. Okay, it's the same thing as maybe a lot of you are not familiar with this notation. You can think of it as any vector a had like a component a1 I plus some a2 j. So this is describing the horizontal component, and this describes the vertical component. And same here, instead of writing something like this, you can go ahead and write a1 and a2. Okay, so that is just a notation describing the function, meaning at any particular time t, when you plug that value t into this function, this vector function, you give out a vector, right? You have a vector whose horizontal component and vertical component is being dictated or being controlled by the function of t. Okay, so how does that would contribute into understanding the length of a certain graph? Now we have this curve, and at any particular point that we set is differentiable, and it has a value, a particular value t. Plug in there will give you a particular vector. So here, let's say you have some here you have some t equal to some I value, and here at this point you have some t equal to I plus 1 value. Okay, it could be anything, I plus any number, I plus a very finite number, can plus a million or anything. Okay, so that the difference or the curve between the 2 points at each particular time will be delta r, right? Or we can call it delta L, meaning the change or the strip of the curve at between any particular time t. At time ti, you have, this is r, this vector right here from the origin to that describe a vector will be r ti and t sub I, and then here at this particular time you have another vector that is r t I sub I plus 1. Okay, alright, so you have two vectors right there. So now how can we go ahead and do this, right? Well, we know something. We know that the derivative, or the instantaneous rate of change of any vector, any particular vector for this curve, right? From 0 to that particular point on the curve, from 0 to that point give you a vector, right? Any point give you a vector. Okay? So therefore, dr, instantaneous rate of change of the vector, not the r itself, but the vector right? The vector, not the scalar, right? So dr over dr vector over dt, that will be equal to the limit as dt approaches 0 r t plus delta t minus r t over delta t. Okay, so this is the definition of the instantaneous rate of change of vector r. Although, well, how do we relate this to this? Well, we know that r vector rt is described by this notation, so therefore you can go ahead and say that d, you can say this is just r prime, right? So therefore r prime of t would just be equal to taking the derivative of the horizontal component and the vertical component, but since they are the function, therefore we just take the derivative of each function. So there we have it. We have dx over dt and dy over dt, right? Okay, so there we have it. But now this is a vector itself because it's in a vector form, right? It's still a vector. It's just that little vector that is tangent to the curve. So one may say, well, let's take the derivative of t equal to I, right? So it's just this tangential vector to the curve right here. Okay, so that is r prime t. Okay, it's just tangential to that point as dt approaches 0. Well, now how do we go ahead? Well, we jot down what we have for the vector r prime t, but how do we connect that into finding the length of this curve? Well, you know that each little increment add up, right? Each little dr add up will be the length of the curve eventually, right? You add up just small piece bit by bit, will become the whole strip, right? Or the whole line. So I'm sorry, the whole curve, not the line. So you have so you're trying to restrict this delta r very small as it approaches 0, right? As it approaches 0, it gets smaller and smaller and smaller. You will have and you take the limit of all of that sum, you will get the finite value for the length of this parametrized curve. Okay. Well, okay, let's just formulate it. Okay, so there, because of what we've been talking about, okay, we try to restrict this delta r into almost 0, so that it become almost like a straight line. So we add up those little straight line like that, add up from some particular point, some point at some t equal to a, and to this endpoint t equal to the b. Just add up little increments like that, just add it up, and eventually we take the limit of that sum. Now you can understand this is just the integral or the anti-differentiation process. So we have this, right? So that's the first step we do. Limiting this into a very small delta r, and then take the limit of it. There you go. There you have a length of the curve. Let's go ahead and do it. So we have L is approximately the sum of some delta r I, and I start from, you're gonna have a boundary, right? I start from 1 to some n. Okay, and how do we determine this n? Well, you can go ahead and have this divided up into many little increments. So n could be anything that you want. N could be 1,000, 1 million, anything that you wish. Okay, so all right. So let's take this. The bigger the n, the more accurate it will be. Okay, so there you have it. The length will be equal to the limit as delta ri approaches 0. Limit I start from 1 goes to some n delta r sub I. Okay. All right. and this is equal to the integral, right? T start from this is delta r, so dr, okay? Some boundary. Well, okay, so now we have that. What do we do, right? So let's say r here start at some t go to a, and r here to b, right? Well, now we have this, right? We have this derivation r prime t equal that, and now we have delta r. One is the vector, one is in the vector function, and one is in a scalar, right? One is a vector and one is a scalar. So how do we connect it? Well, we know that all it is just taking the magnitude of it. You know, a vector is defined by its direction and its magnitude. So we got its direction down, all right? So all we care about is the for this to become this, it's just the magnitude. Okay, so we just take the magnitude of it, which is, you may go substitute for t, you know, for r, for what t could be, so that it become ra, t equal a, right? What t could be so that r become b, it's b. Okay, just plug it in. It's the entire process of it. So you can put this as dr dt times dt, right? It's in terms of dt. Well, now this become the scalar, right? This is in another cell, it's just a scalar of this, right? This is just a scalar of that thing. So it equal to a would be scalar of r prime t, right? dt. Alright? Okay. So this notation is meaning for the scalar notation, and you can go ahead and just transfer that to this one. A scalar of any function is just applying the Pythagorean theorem. So that would be so we change all this scalar vector, and especially it's in 2D, two dimension, will be dx over dt square plus dy over dt square dt. Alright? So this is your general form to calculate the length of a curve, right? This will be this equation. Alright? Thank you very much.